Allow me to call your attention to the background image here for our objective on being able to investigate, derive, and use the chain rule. You got a bunch of gears for some reason. Why is that? That's because if you take a look inside just about any calculus book, in the section related to chain rule, you're going to see some kind of machine similar to this one. You got gears within gears. Okay, so let's maybe zoom in here just a little bit. Now, you've got basically 3 axles and 4 different gears, and you have a crank handle right here, and you're turning this axle 1, which is going to turn gear 1. Gear 1 is going to then drive gear 2, which turns axle 2, attached to gear 3. Gear 3 is then going to drive gear 4, which is attached to axle 3. Okay, all right. So far, so good? Okay, so in the set of gears, notice that you would have to rotate axle 1 3 times to rotate axle 2 once. Does this make sense? Notice that the radius here is 1 for gear 1, and the radius for gear 2 is 3. So, in other words, the circumference of gear 2 is going to be 3 times as big as gear 1. So I need to spin it 3 times just to get gear 1, gear 2 to spin around once. When it spins around once, then that's going to spin around this gear 3, okay? Further, you have to rotate axle 2 twice to rotate axle 3 once. So, gear 3 also has a radius of 1. It matches up with this gear 1 over here. And gear 4 has a radius of 2. In other words, the circumference of gear 4 is twice as big as the one for gear 3. I have to spin this around 2 times in order to get gear 4 to rotate around once. Okay, so here's the question. How many times would you have to rotate axle 1 over here to get axle 3 to rotate just 1 time? Okay, this is an example of a composition of functions because the output of gear 2 becomes the input of this gear 3, which is driving gear 4. So we said that it's going to take 3 spins of gear 1 just to get gear 2 to spin around once. Okay, but it's going to take gear 3 2 spins to get gear 4 to spin around once. And if I wanted to know how many times I have to turn this crank handle at axle 1 to get gear 4 to turn around 1 time, it's going to be this rate, which is 3, times this rate, which is 2, to get 6. It takes 6 cranks of this handle to get gear 4 to turn around once. And this is an example, again, of a composition. And if I'm dealing with rates, it's taking derivatives, and notice that what we had to do is some kind of multiplication. Okay, so this kind of static picture here only goes so far. So in the next little video, I'm going to show you a little demonstration of doing this with some Lego pieces, maybe bring it all together. But the main takeaway here is that we had to multiply the rates together. Okay. All right, so we're going to also do, in just a minute here, an investigation, which again has to do with taking the derivatives of composite functions or a composition of functions. So dismantling this g of x function, which must be performed first, that's our interior function. And then the f of x is our exterior function. Whatever the output of the g of x function is, it goes into the input of the f of x function. So we're going to investigate what happens to the inner and outer functions when we differentiate.